welcome to all of you in the next class of this course. So, in yesterday lecture we were discussing about Fourier series. So, let me continue with the same topic, what is Fourier series. Fourier series. So, in last lecture we were taking function which belongs to this space. So, let us have some knowledge about this space. This is a set of this is a space of all square integrable function. It means if f belongs to L2 0 and dx is less than infinity. Okay. So, moreover, one more condition which we have written on this space is means function which belongs to this space is a periodic function of period 2L. All of us know what is the periodic function. So, it means f of x will be f of x plus 2L for all x belongs to R. Now, in the last lecture I have written this as a Fourier series, okay, where CKs are called Fourier coefficients. So, if you look at just for simplicity I am considering L is equal to pi. In that case this expansion will become I kx. Okay. So, here you look at one thing that e to the power I kx gives you an orthonormal basis for a space 0 to 2 pi for different k belongs to z. Or here basically we are writing k is equal to 1 to infinity, or sorry, minus infinity to infinity. Okay. K is minus infinity to infinity. So, if you look at this space more carefully, how we are generating this space? If I denote this function by this. So, basically this is let us say Wx. So, this is a dilation of a simple one element. What is that one element? That one element is e to the power iota x. So, we are generating whole space by dilation of a single function which is this function. Okay. So, this function is by dilating this functions we are generating the whole space L2 0 2 pi. So, you should notice that there is a dilation property. Later on when we will connect this to the Fourier series to the wavelet series. So, you will see that dilation will also be in the wavelet series. So, at that point of time we will continue with this dilation property, and that is the motivation that right now I am mentioning you that property. Okay. So, now as this L2 0 2 pi is a cube with norm and inner product. What is the inner product on this space? Inner product is given by this definition. Okay. This is the inner product cubed on this space, norm is this space. So, this is the definition of a norm on this space, this is the definition of a inner product on this space. Now, the next question comes, why we are considering function belongs to this space. Okay, that is the questions. I can, so now can I write a Fourier series for a function which does not belongs to this space? Of course, you can write down Fourier series, but the question comes, what will be, because it is a infinite series, f of x, you know, it is a infinite series. Okay. So, it is a infinite series. So, infinite series may converge or may not converge. So, and when we talk about the convergence of a infinite series, the notion of a convergence are also different. There are different notion of a convergence of a infinite series: uniform convergence, pointwise convergence, L2 sense convergence. So, I am not mentioning all of that notion of a convergence in detail, but what I am doing right now, I will tell you what is L2 sense of convergence. What is L2 sense of convergence? So, for that reason I am denoting the partial sum. Okay. So, this series is said to converge in L2 sense provided this property, this tends to 0 as n tends to infinity. This is the meaning of L2 sense of convergence. So, basically error is f x minus s n x is the error between the function and its partial sum, which is tending to 0 in L2 norm. That is the meaning which you could observe from the given formula. So, that is the if function belongs to this space L2 0 to 2L, only then we can guarantee that Fourier series will converge at least in L2 sense. This is this is basically a theorem. The proof of that theorem can be seen in any standard partial differential equation text where Fourier series is explained in detailed way. So, okay, I have given you very brief explanation of this L2 sense of convergence, because if you are writing an infinite series, you should be sure in what sense it is converging. Okay. So, now the one of the very, I should say, disadvantage of Fourier series I am going to explain, and what is that disadvantage? That disadvantage is Gibbs phenomena. Gibbs phenomena. Okay. So, what is this Gibbs phenomena? Let me explain you with the help of a one function. Function is given like that. Okay, this is the function. If you want to look at the graphic, this will be x, so 0.5, 0, 1. Okay. What you see in how, if I wanted to approximate this function, what will I do? I will approximate this function with the help of this partial sum S n x, which is given by this formula. Okay, for different values of n. So, for different values of n means n 16, I can try for n is equal to 32, n is equal to 64. So, that you can also implement in a MATLAB by Fourier approximations, and once you compute S n x for n is equal to 16, 32, 64, what you will observe that as roughly I can give you a plot for n is equal to 16, this will be like this. For n is equal to 64, this will be more closer. Okay. So, what, as you keep increasing the n, what will be the observation, that wherever the function is has some smoothness, it is okay. function, this approximation will be close to the exact value of the function, but if function is non-smooth near at x is equal to 0.5. So, at this point how large n you take, some oscillations will always be there and this will be spreaded throughout the domain also. Means oscillations will be less for let us say n is equal to 1000, 2000, but you will not be able to remove these oscillations at any cost. Okay? And why this is happening? Because this is happening because of the non-smoothness discontinuity at x is equal to 0.5. Okay? So, this should also be 0.5 or that also less than sign should also be okay. Okay, because at x is equal to 0.5, because there is a discontinuity in this function at x is equal to 0.5. So, when we are taking a infinite sum of this exponential functions, then we are able to resolve this discontinuity. That is what this Fourier series says. But once I am working with a finite sum k is equal to minus n to n, we are not able to resolve this discontinuity properly. Okay? And because you know fx is a discontinuous function and we are writing that function with the help of a sine and cosine, exponential iota x is sine and cosine which are a continuous functions. So, finite sum of a continuous functions cannot give you discontinuous function, and that is one of the main drawback of the Fourier series, which is called in terms of a Gibbs phenomena. Okay. So, this is Gibbs phenomena I have already explained you. So, now what we do that I can tell you, as n tends to infinity it will be more closer. So, this as I am saying, this is a disadvantage of a Fourier series, and later on I will show you that this disadvantage is not in wavelet series. That is why wavelet series is better than Fourier series, because this Gibbs phenomena is completely removed in wavelet series. Okay. So, that is and now one of the other thing which Fourier coefficient satisfy this relation which is called Parsable relation. Okay, which is called Parsable relation. This is also very famous relations if you, okay, because if you remember earlier we were also talking some conditions, but this is also one of the, like if you remember when we were discussing orthonormal basis, Rees basis, we were writing some conditions. Ck is basically f comma f inner product of f with Vk, which Vk's are exponential of Ikx. Okay. So, this is also what is the coefficient of Fourier series are satisfying. This relation is called Parsable relation. So, now from Fourier series I was writing for a function which has a period 2L, but now if L tends to infinity, means period tends to infinity, Fourier series is converted to a Fourier integral. Okay. And complex form of Fourier integral is called Fourier transform. Complex form of Fourier integral in a short form is called Fourier transform. Again, in short form Fourier transform can be written with Ft and Fourier series can be written with Fs. So, now let me define what is Fourier transform, because first I will define you Fourier series, Fourier transform, and then wavelet series, wavelet transform. That is the sequence, because only then you will be able to appreciate the beauty of wavelet analysis over Fourier analysis. So, now what is Fourier transform? Now, I am defining a Fourier transform by this formula. For f belongs to L1 R. We have already seen this kind of a spaces L1 R, L2, LP R for P general greater than equal to 1. So, I do not need to redefine again what is this L1 R spaces. So, this is a Fourier transform of a function f x which belongs to L1 R. This is a improper integral. So, if I am talking about infinite series improper integral, I also have to talk about convergence of them. So, for that reason I am taking f belongs to L1 R, because if f belongs to L1 R, this Fourier transform always exists. That I can show you also. What will be this thing? This thing will be, so this is basically, if you look at, this is the this norm. So, if f belongs to L1 R, this is less than infinitive. So, it means Fourier transform exists. This improper integral converges. So, that is why we are working out with f belongs to L1 R. Now, we will study first of all, let me give you physical interpretations why we study Fourier transform. Why we study? Sometimes we want to analyze functions for mathematicians, signals for engineers in a domain with respect to the frequency, okay? Because you know what Fourier transform is doing? Fourier transform is decomposing the function into the various waves. So, sometimes if we want to analyze the function in different domain, and what is that different domain? That different domain is called frequency domain, and then Fourier transform is also sometimes called Fourier spectrum. Okay, Fourier transform is called also Fourier spectrum. We analyze what is the need of it? We analyze the functions in a different domain which is called a frequency domain, and Fourier transform is also called sometimes Fourier spectrum. So, now we will study different properties of Fourier transform which will be used subsequently. So, if I say f dash x is also in L1 R, then one of the property I can prove is this. What is this? E to the power minus I omega f dash of x dx. That is why I have chosen this f dash x is an L1 R, because only then I can define this, I can talk about the existence of a Fourier transform. So, if I use integration by parts, so we are using integration by parts where, so this is I omega f x of dx, okay. This is an L1 R function. So, L1 R functions always tends to 0 at x tends to plus minus infinity. That is the property of a function which belongs to that spaces. So, basically this is I omega f at of omega, okay. So, in a nutshell, this is a famous property of the Fourier transform. From this property we can deduce one more thing, f hat of omega tends to 0 as omega tends to plus minus infinity. This can be proved directly from here, because once you write down this in the left hand side, this is very much clear. This property we will use later on, that is why I have defined here. And the next property of this Fourier transform is, yes, this is now if we know from one domain we are going to the frequency domain, we should also know how to come back, otherwise there is no point of defining some integral transform. Fourier transform is also integral transform, as you must have already studied in earlier. So, now we are defining a inverse Fourier transform. So, inverse Fourier transform we are defining by this formula, provided f hat is omega is also in L1 R, because only then we can again talk the convergence of this improper integral. Okay. We can talk, that is why we are choosing f at omega belongs to L1 R. It is not always necessary that if f x belongs to L1 R, f at omega will also be L1 R. That I can show you by one example. I am taking one function 0 otherwise. Okay, this is the function I am taking. So, I am defining what will be the Fourier transform for this function. So, this will be 1 plus I omega. Okay. So, if you look at, now we have to define whether this function is in L1 R or not. This is the Fourier transform of this function. So, I have to choose whether this function is not in L1 R. So, I can take these functions separately. So, of course, this is not an L1 R function. Okay. So, I have given you this by one example, that if function is in L1 R does not necessarily mean f at omega may not be in L1 R. Okay. So, that is why whenever we were defining a inverse Fourier transform separately, we were making this assumption. So, now we are looking at the Fourier transform of one another functions, which all of you must have seen earlier, and that function is called a Gaussian function. This is called Gaussian functions. We are defining a Fourier transform of this function. So, how I can write down a x plus I omega, I can always add this, add and subtract something. So, using that terminology I have done that. So, now I can take this term common, okay. So, what how now we have to simplify this integral as well, whole thing x plus I omega by 2a whole square, I can take t. So, then after substituting this we will get e to the power minus t square dt. Okay. So, this is, now we have to calculate this integral. We all know this is under root pi, but if you will ask me how to calculate, because we do not know the antiderivative of this function, that is why some, in that case some special techniques are devised to calculate this kind of a integral, and based on Taylor series etc. That is just for your knowledge. So, f at omega will be under root pi by a e to the power minus omega square by 4a. Okay. So, this will be the Fourier transform of a Gaussian function. Sorry, this under root sign will be, because this value is under root pi by under root a. So, what do you observe specifically about the Fourier transform of a Gaussian? Can you think for a while? The main point is that Fourier transform of a Gaussian function is also in the form of a Gaussian. This is also a form of a Gaussian. That is the specific point to observe, which we will exploit later on, that Fourier and we will work out with this Gaussian functions, because the Fourier transform of Gaussian is again a Gaussian functions. So, this is an important point which all of you should note for a future lectures. Now, I am coming to define another concept which is used in some of the analysis, which is called convolution. Okay. So, I am defining what is called convolution. Okay. Convolution of a two functions is defined in this way. Okay. So, what we are doing? We are multiplying the function f with the function g, not exactly with delayed by parameter tau, sorry, this should be tau. Okay. And then we are multiplying this function with the delayed by tau to the another function g, and then we are integrating with respect to this delay parameter. This is how convolution is defined. Convolution is very important, it has lot of applications in electrical engineering, probability stats etc., many applications, and I assume all of you must have heard about this already. So, this is how we define convolution, but again this is an improper integral. So, I have to talk when it exists. So, for that reason I am saying if f and g belongs to L1R, then convolution will also be in L1R. This is just a one line proof, because this will be equal to f of tau g of x minus tau d tau dx. Now using Fubini's theorem you can very well, because f and g both are in L1R, you can very well prove that f and g will also be in L1R. It means f and g norm is, sorry, this is a convolution. Okay. So, the next property of the convolution which we can prove, that convolution is also commutative. That is also, this you can take it as an exercise and you can prove it by change of variables, that convolution is a commutative property for all f and g belongs to f and L1R. It is also distributive. Will be equal to f star of g of h for all f g h belongs to L1R. Now the next question is identity operation also exist for a convolution? It means f for all f belongs to L1R. Does identity exist for a convolution operator? This is my next question. Okay. So, can you think for a while for this? Does identity exist for a convolution operations? You think, in the meantime I am proving one another theorem which I will be needing to answer these questions. Does identity exist for a convolution operation? And that theorem is called convolution theorem. Convolution theorem. What this theorem says? This theorem says that f and g belongs to L1R, then this will always be the case. I will prove this statement. Okay. Okay. Now I am using Fubini's theorem. F of tau dx into d tau. Okay. Now I am using a change of variable x minus tau is equal to y. From this step to this step we have come using the Fubini's theorem. Fubini's theorem. How order of integration, basically in a nutshell this theorem says that how order of integrations can be changed. Okay. So, this I can split into two terms and then f of tau e to the power minus I omega tau I omega y g y dy and d tau. So, basically you can see this is equal to f hat omega g hat omega. Okay. So, we have proved convolution theorem. It is a very beautiful theorem because it has many applications. One of the application is it helps us in computing the convolution with the very reduced complexity, because otherwise how will you compute the convolution? You will compute this convolution with this definition which I have given you here. Okay. But with the help of this convolution theorem, what you are doing, I can compute the convolution with this. Inverse Fourier transform of f at omega g at omega. Okay. So, complexity is reduced if I am computing the inverse Fourier transform of multiplication of two function f at omega and g at omega, and then I am computing the convolutions instead of going with the direct definitions. Okay. So, and convolutions has many applications, and we will be using this convolution theorem to support my answer of my previous question, that does identity exist for a convolution operations. Okay. So, how? Because now in the left hand side I will be using convolution theorem. So, it means I am taking the Fourier transform of this both sides. So, this will give me this by using convolution theorem, which implies E hat omega is 1. So, is it possible? Can you think? Is it possible? No. Existence of an identity means there exists a E belongs to L1 R. Existence of identity means there should exist E which belongs to L1 R which satisfy this property. But here we are saying E hat omega is equal to 1, which is not true. Why it is not true? Because if any function which belongs to L1 R space, it should tends to 0 at x tends to plus minus infinitive. So, means if E hat omega is 1, it means, if you remember, I have used, not I have used, I have proved one property here. F at omega should tends to 0 as omega tends to plus minus infinitive, okay, for a function which belongs to L1 R. So, there E belongs to L1 R. So, Fourier transform should, and because of that reason I proved this property, as I said I will use this property later on. So, Fourier transform of this should tends to 0 as omega tends to plus minus infinitive, but there it is, just a minute, but you look here, this is not this, according to the previous property of a Fourier transform, this should tends to 0 as omega tends to plus minus infinitive, but this is contradictory. So, it means there does not exist convolution identity, or we have to say something more how we can approximate this convolution identity. And with these words I am closing my today's lecture, and whatever exercise I have asked you to prove about convolution operations, you could look at the proof of them, because it really helps. And in next lecture, what we will do, we will tell you how to work out with the approximation of the convolution identity. Okay, thank you very much. With this, I am closing my lecture.